So in our last class, we were discussing this approximation of equivalent circuit, and we have got two equivalent circuits. One is excluding the primary leakage impedance drop due to exciting current. Another is including secondary leakage impedance drop due to exciting current. Okay. And these two circuits are as shown in figure 6a and 6b. So first one is excluding primary leakage impedance drop due to exciting current, and second one is including secondary leakage impedance drop due to exciting current. Okay. Now still further simplification is achieved or can be achieved by neglecting the shunt branch parameters, that is RC and XC. As I have mentioned earlier, that this exciting current is about 2 to 6% of the total rated primary current. So it is very less in comparison with the total current. So we can neglect the exciting current. Therefore, if we neglect the exciting current, which means we can neglect these shunt branch parameters also. So in both the cases, we will get a more simplified circuit as shown in figure 6c. Okay, so in this circuit only the series branch parameter are shown, that is total equivalent resistance is equal to R1 plus R2 and total leakage reactance XE is equal to X1 plus X2. So these two parameters. Okay, so this is a very simple circuit which can be achieved by neglecting the shunt branch parameters, that is by neglecting the exciting current. Now this simplification is valid for transformers which are having the power rating say over 100 kVA. So 100 kVA power rating. So any transformer which is having power rating of 100 kVA or more, then we can apply this kind of simplification. Okay, because for this type of transformer having this higher rating of power, this neglecting I mean the for this kind of transformer which are having power rating 100 kVA or more, in those cases only the exciting current can be neglected. For transformers having power rating less than 100 kVA, this IE cannot be neglected. Okay, it in that case it will be comparable with the rest of the primary current, that means the other component of primary current, which is the load component. Okay, so in that case we cannot neglect IE, so we have to use the exact equivalent circuit or exact equivalent circuit or the simplified version which we have achieved by including or excluding this primary leakage impedance drop and secondary leakage impedance drop due to exciting current. Okay, so up to this we can this equivalent circuit we can apply for transformer rating which is having power rating less than 100 kVA, and this approximation, that means this circuit can be used for transformer rating having transformers having power rating greater than 100 kVA. Now for transformers having power rating more than 500 kVA can still be further approximated by neglecting this winding resistance Re, because in that case this equivalent resistance Re is quite small in comparison with this equivalent leakage reactance Xe. So KVA rating transformers with KVA rating 500 kVA or more, in that case Re is less than Xe. So we can neglect this Re and we will get a more simplified equivalent circuit as shown in figure 6D. Okay, so here we have only the leakage reactance, no winding resistance. Okay, so this is the most approximate equivalent circuit, and in case of large power system, we can apply, or we can in case of while modeling any large power system, we can use this simplified approximate equivalent circuit. That means the transformer will be replaced or will be denoted by this leakage reactance only. No other components are required. Okay, so in case of large power system means which deal with a very large amount of power, in those cases we can simply replace the transformer by this equivalent circuit only. Okay, is it clear? Any question?
No, sir.
Okay, so that is all about this equivalent circuit. So let us solve one numerical problem based on this phasor diagram. So here a transformer is given with voltage rating as 2200 volt by 220 volt, 50 hertz, single phase transformer, has exciting current of 0.6 ampere and force of 361 watt. When its high voltage side is energized at rated voltage, calculate the two components of the exciting current. Okay, so high voltage side, that means the voltage, the side which is having voltage rating of 2200 volt, that side is energized. That means, so this 2200 voltage side is the primary side, and this 220 volt side is the secondary side, and the exciting current is 0.6 ampere and core loss is 361 watt. So we have to calculate the two components of exciting current. IE having two components, one is IC, another is IM. So we have to calculate this IC and IM, while IE is given, core loss is given. Okay, so this is question number A. And in the second part or B part, if the transformer supplies a load current of 60 ampere at 0.8 power factor lagging on its LV side, then calculate the primary current and its power factor. Ignore leakage impedance drops. So ignore leakage impedance drops. That means there is no winding resistance, no leakage reactance in the primary side or secondary side. So Re1 and Xe1 both are equal to 0, or we can write R1 equal to 0, X1 equal to 0, R2 equal to 0, X2 equal to 0. So using this information, so we have to draw the phasor diagram, then we have to calculate the primary current. Okay, so let us proceed. First of all, write down all the given data. So exciting current I is 0.6 ampere, supply voltage V1 is equal to 2200 volt, which is equal to V1 dash. Why is this? So why V1 equals to V1 dash?
Sir,
Tell me.
Because R1 X1 is 0.
Yes, primary leakage impedance is 0. So V1 equals to V1 dash. Core loss is given, PC equals to 361 watt. So how can we calculate this core loss current IC? So therefore the core loss component of exciting current IC can be calculated using this formula. IC equals to PC by V1 dash. So here V1 dash is equal to V1. So calculate IC. 361 divided by 2200 volt. So how much is IC?
0.164 ampere.
0.164 ampere. So once we get this IC, we can calculate IM. How? What will be the formula to calculate IM?
IE minus IC.
Or can you
I
calculate
square minus
IM
IC square
using
root over
algebraic formula, algebraic equation?
I
No, sir,
square
phasor.
minus IC square root
Phasor,
over.
phasor.
Yes, they are phasors. So we cannot use this formula. We cannot use this one. So IM will be equals to root under IE square minus IC square. So calculate this. What is IM?
Zero point 0.577.
Yes, 0.577 ampere. So part 1 or part A is completed. Okay. Any doubt? Anyone? So please note that we cannot use this equation because this IM, IC are phasors. So you cannot, and IE also, all these currents are phasor currents, so we cannot use algebraic equation. We have to use phasor equation, that is IE equals to IM phasor plus IC phasor. So therefore we have to use this equation. Okay, IM is equal to root under I square minus IC square. Here the magnitude of IE will be given by root under IM square plus IC square. So using this equation we can calculate IM equals to this. Okay. Now the second part. So here load current is given. So load current means I2. So this is the phasor diagram for this problem. So a lagging power factor is given. So I2 lags V2 by an angle of theta 2, which can be calculated using this 0.8 power factor. Okay, so cos theta 2 is equal to 0.8. From that we can calculate theta 2. I2 is given 60 ampere. From that we can calculate I1 dash. We know the value of IE and I1 dash is calculated. So we have to find this I1 and then this power factor angle theta 1 and then power factor cos theta 1. Okay, or you can calculate cos theta 1 directly. Okay, so if IE and I1 dash are known, after calculating I1 dash from I2, so how to calculate I1? Any idea? If the angle between I and I1 dash is known, then it is very simple. Suppose this angle is known, then it is very easy. You can apply the vector addition formula to calculate I1, but this angle is not known. In that case, how to calculate I1?
So we have to calculate I1 dash.
I1 dash, suppose calculated from I2, then tell me.
Sir, we need the angle.
I
right?
and
So-
I1 dash are known. So tell me how to calculate I1.
So for that angle, we can do like 90 minus alpha minus theta 2.
90 minus alpha minus theta 2. Yes, that way we can do, or we can resolve this I1 dash and I into perpendicular components, that is
Yes,
along
sir.
V dash and along phi n. Okay, and then add the x components and y components, and then find the resultant of those two components to get I1. Okay, in that way also we can calculate. So from phasor diagram, I1 dash N1 equals to I2 N2. So therefore I1 dash is equal to N2 by N1 into I2. So I2 is 60 ampere, N2 by N1 is actually V2 by V1. N2 by N1 is equal to V2 by V1. So what is V2 and what is V1 here?
V2 is 220
and
and
50 volt.
Yes. So use that to calculate I1 dash. So how much is I1 dash? Very simple, 6 ampere.
6 ampere.
Okay. Now load power factor is given 0.8 lagging. So cos theta 2 is 0.8. From this calculate sin theta 2.
0.6.
0.6.
Yes. Now the vertical component of I1. Vertical component of I1. That means if we draw one line, so this component from this point to this point, this component is actually sum of vertical component of I1 dash and vertical component of IE. That means this part plus this part. So this part is IC, which we have already calculated, and I1 dash, vertical component of I1 dash is nothing but I1 dash cos theta 2. If this angle is theta 2, then this angle is theta 2. So I1, vertical component of I1 is equal to I1 cos theta 1, which is I1 dash cos theta 2 plus IC. Is it okay with everyone?
Yes, sir.
Yes, sir.
Any doubt? Okay, then calculate I1 dash cos theta 2 plus IC. I1 dash is known, cos theta 2 is known, IC is known. 6 into 0.8 plus 0.164.
4.9.
4.964.
4.964 ampere. Then find out the horizontal component, that is I1 dash sin theta 2 plus IM. Isn't it?
Yes, sir.
So calculate this one. 6 into 0.6 plus 0.577.
4.177.
Now calculate I1. So I1 equals to root over this root over this square plus root over this square.
Six 6.487.
6.47. Okay, no problem. Now how to calculate power factor?
Ratio of apparent power by real power.
No, we don't have those informations.
We need to find then cos theta 1, right?
Yes.
I1 cos theta 1 divided by I1.
Yes, obviously. So primary power factor cos theta 1 is equal to I1 cos theta 1 divided by I1. So we have I1 cos theta 1, that is the vertical component of I1, and we have already calculated I1, this value. So find this ratio, you will get cos theta 1. Isn't it?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So 4.964 was I1 cos theta 1 and 6.47 is I1. So power factor is 0.766 lagging. Any doubt?
No, sir.
So here phasor diagram. First of all, you must know how to draw the phasor diagram of a single phase transformer at lagging power factor, unity power factor and leading power factor, showing all the important or main parameters like the exciting current, primary current, load component of primary current, then the two components of exciting current, flux, two induced EMFs, then primary voltage, and how this primary voltage is determined using this opposite of E1 and the primary leakage impedance drop, and also you have to show the secondary leakage impedance drop. So showing all these things, primary power factor, secondary power factor, etc. Okay. So now showing all these things, you must know how to draw the phasor diagram of a single phase transformer at no load, at lagging power factor load, unity power factor load and leading power factor load. Now after that, you have to know how those phasor diagrams can be modified for a given condition. Like in this problem, all the leakage impedance drops are neglected. So how to modify that? How to modify the phasor diagram for this, for any given condition? Okay, that you have to understand. Am I clear? Okay, that's all about this equivalent circuit and phasor diagram. Now, next topic is per unit representation of transformer parameters. This is one very important topic. Normally, while studying any large power system, we generally apply this per unit calculation. Okay, so all the calculations are done using these per unit quantities. Okay, there are certain advantages of using this per unit quantities. So for electrical machines or electrical machine systems, that means suppose any power system which contains different types of electrical machines like the generator, the transformer to step up or step down the voltage level, and as a load some motors like induction motor, even synchronous motor also. So any system which contains this kind of electrical machines, the different types of calculations are commonly done using this per unit quantities. Okay, so for any system, the per unit values are obtained by choosing a set of certain base values which can be chosen arbitrarily. Okay, now what are these base values? It will be more clear if we first define what is per unit, what are per unit values. Okay, so another information is here, that is normally the rated quantities of any device are taken as the base values. So what is this base value? First of all, let us define the per unit quantity. For any per unit quantity can be defined using this equation or this statement. So per unit quantity is equal to actual value of the quantity in any unit divided by the base value of that quantity in the same unit. So suppose we are defining the per unit quantity, per unit impedance of any transformer in the primary side. Suppose Z E L. So low voltage side equivalent impedance. That means while we are calculating the equivalent impedance from the low voltage side, that means all the secondary secondary leakage impedance is referred to primary side, and then we have taken the total. Okay, so ZEL. If we want to calculate the primary low voltage side per unit leakage impedance, then what do we have to do? In that case, we have to take the actual value of this quantity. That means suppose ZEL is given 20 ohm. Okay, now we have to select one base value, that is suppose the rated value, rated impedance, suppose Z E. This is the rated impedance of the transformer. For example, suppose this is equal to 40 ohm. Okay, so we have to select one base value in the same unit, then we have to take the ratio of this two. That means the actual value 20 ohm divided by the base value, then we will get the per unit value, which is 0.5. Now see, the per unit quantities are unitless because they are the ratio of two similar quantities. Okay, so in this way we have to define per unit quantity. So normally these base values of any system are taken as the rated quantities. So in case of transformer, the rated quantities are primary side voltage, secondary side voltage, power rating, that is kVA rating. So these are the rated quantities. So we have to take the base quantities as these quantities only. Okay, so let us see. So let the subscripts capital B, capital L and capital H denote base low voltage side and high voltage side respectively for a single phase transformer. So if we write ZL, it means the low voltage side impedance. If we write ZH, that means it is the high voltage side impedance. Similarly, if we write ZB, then it means base impedance. Okay, so B for base, L for low voltage side, H for high voltage side. Now let us consider consider the high voltage side first. So for high voltage side, base voltage, that is the given that is the rated voltage of the transformer. So base voltage is equals to rated voltage on high voltage side. So it is denoted by VBH. B is to denote base quantity, H means high voltage side parameter. Okay, so VBH is the base voltage of the high voltage side. Okay, base current IBH, same notation, rated current on high voltage side, that is equal to, now here normally in a transformer nameplate this current rating are not given. First power rating is given in kVA, then two voltages are given, V1 if we consider this as the primary, so V1 V2 are given. Okay, so if kVA and these voltages are given, then we can calculate the two sides current, rated current. So that is why IBH is equals to transformer rated VA. So kVA to volt ampere by multiplying it by 1000 and divided by that VA rating. If you divide that VA rating by rated voltage on high voltage side, then you will get high voltage current. Okay, high voltage side current. So in this way you have to calculate the current for any particular side. Is it clear?
Yes, sir.
Yes, sir.
So now we have VBH and IBH. So we can calculate the base impedance, because base voltage and base current we are having. So base impedance will be equal to VBH by IBH applying Ohm's law. So ZBH, that is the base impedance from high voltage side, which is the ratio of base voltage and base current of high voltage side, and this is in ohm. Okay, so base quantity and actual quantity, these are expressed in similar unit. Remember this. So and ZBH can also be expressed in this way. If we multiply this VBH and IBH both by VBH, then we get VBH square by VBH IBH, that is the kVA rating or VA rating. So that is rated voltage on high voltage side square by rated VA. See, as I have mentioned, normally nameplate data are these parameters. Okay, so if you want to calculate the base impedance directly using these parameters only, then you can apply this formula. You don't have to calculate IBH. Right? Am I clear?
Yes, sir.
Yes, sir.
Okay, so base impedance ZBH can be calculated using this formula: rated voltage on high voltage side square divided by rated VA. Okay. Now this winding resistance, leakage reactance and leakage impedance from the high voltage side. See, these are the equivalent resistance calculated from high voltage side. So REH, what is this actually? REH is actually RH plus RL into NH by NL whole square. We have referred this RL to the high voltage side. Right? Similarly, we can write a similar expression for XEH, that is XEH is equal to XH plus XL into NH by NL whole square, and same expression for ZEH also. Okay, so if we want to calculate the per unit values of these quantities, this formula is applicable to all these three. If you want to calculate REH, then you have to take actual value of REH and you have to divide it by ZBH. If you want to calculate XEH, then you have to take actual value of XEH divided by ZBH. Okay, so this formula is applicable to all the three quantities. Right? Got my point?
Sir, here ZBH is the base value we are considering.
Yes, ZBH of high voltage side. Here we are calculating all the parameters from high voltage side. So REH is the equivalent resistance referred to high voltage side. XEH is the equivalent leakage reactance referred to high voltage side, and ZEH is the equivalent impedance referred to high voltage side. ZEH can be calculated using the formula ZH plus ZL into NH by NL whole square, or it can also be calculated using this equation, that is, you have already calculated REH and XEH directly, so you can directly use this one also, REH plus J XEH. You have calculated REH using this formula and XEH using a similar formula, so you can use this expression as well as you can apply this equation to calculate ZH. Am I clear? If anyone having any doubt, you can ask. These transferring parameters is very important for this chapter, or referring. You have to understand this very clearly.
Sir, what is the subscript PU?
Yeah.
Per unit?
PU means per unit.
Sir, what is the use of per unit?
That I will show later. First of all, let us define these per unit quantities. There are certain advantages using these per unit quantities. Okay, I will say later on. First of all, have you understood these things? Tell me that only.
Sir, one doubt. Sir, for voltage, if we are finding the per unit of V1, then we will use VPH.
Sorry, repeat
Sir,
again.
if we are finding the per unit value of any other criteria, like this one here, we are finding only criteria whose units are ohm. If you are finding some criteria with unit volt or ampere, for that we will use VPH and IBH.
For high voltage side, you have to use VBH. But see, suppose this one is VBH and this one is VL. Okay, so VBH and this VH, they are same, so per unit value will be 1, isn't it? We have taken the base voltage of high voltage side as the rated voltage on high voltage side. So this value and this value are same basically. So if you take the per unit value, you will get 1.
Yes, sir.
Okay, let us see from the low voltage side. So for low voltage side, again we can define the base voltage as the VBL, rated voltage on low voltage side, base current IBL, that is rated current on LV side, which can be calculated using this formula, transformer rated VA by rated voltage on low voltage side. See, this rated voltage, rated VA, this is common from both sides. Okay, only his voltage will change. That is why we will get different current from two sides, as well as this different voltage from two sides, right? So base impedance ZBL equals to VBL by IBL, which can be expressed as rated voltage on low voltage side square divided by rated VA. Then we can write the similar expression, that is REL, XEL, ZEL in per unit is equal to actual values of those quantities divided by ZVL. Again, this
Sir, in the
REL,
last case, it is not
sorry,
up to SN. Sir, in the last case, while we are calculating REL, it is not up to SN. It's ohm by ohm cancellation.
no. What are you saying? Please repeat.
Sir, I am in the last part REL. While we are calculating REL, we are dividing ohm by ohm. So unit cancels and it becomes constant.
And that I have already mentioned. The per unit quantities are baseless, unitless quantity, because here we will divide or we will take the ratio of two similar quantities. That I have already mentioned. What is your question?
Sir, that's only my question, sir. I've cleared it.
Per unit quantities are unitless. Okay, so here REL is equal to RL plus RH into NL by NH whole square. Similar expression can be written for XEL as well as ZEL. Okay, or ZEL can be written as REL plus JXEL. Right? So in this way we can calculate REL, XEL and ZEL. Then we have to divide those quantities expressed in ohms by ZBL, which we have calculated using this expression. So we will in every case we will get the per unit quantities, per unit values of REL, XEL and ZEL which are without any unit. Okay, so base quantities are unitless quantity. Remember that. Okay, so now ZEL in per unit is equal to ZEL in ohm divided by ZBL, as we have seen in the previous expression. Now if we multiply this ZEL and ZBL both by IBL, so what is this ZEL and IBL? That is the leakage impedance drop at rated current. See, voltage drop across ZEL at rated current, and ZBL, IBL, this is base voltage on the low voltage side, which is the rated voltage of low voltage side. As we have selected the rated quantities as the base quantity, so VL is equal to VBL. Okay, sorry. So voltage drop across ZEL at rated current divided by the rated voltage will give you the ZEL in per unit. Okay, so what is the advantage of this expression? What we can get, what information we can get from this expression? We can directly calculate the voltage drop across any leakage impedance if the per unit values of that leakage impedance is given. See, for a single phase transformer having this as the voltage rating, so 2300 volt by 230 volt, so high voltage side voltage rating is 2300 volt and 230 volt is the low voltage side voltage rating. Now if this transformer is having ZEH is equal to 0.03 per unit, so ZEH is equal to 0.03 per unit. That means high voltage side leakage impedance is its value in per unit is equal to 0.03 per unit. Okay, So which means the voltage drop across the high voltage leakage impedance. So this is actually ZEH per unit. Okay, but you can express it as it is given here, that is ZEH is equal to 0.03 per unit. If you write the unit in per unit, then this expression is okay. Otherwise you have to write ZEH in per unit is equal to 0.03. Both these notations are correct. Okay, so suppose any transformer having this voltage rating and its per unit impedance from high voltage side is 0.03, which means we can calculate the leakage impedance drop directly using this 0.03 per unit value. So 0.03 per unit means 3%. 3% means 3 into 2, 3% of this high voltage side voltage reading. So leakage impedance drop will be 3% of this 2300 volt. So we can directly calculate that using this per unit value. Is it clear?
Yes, sir.
Yes, sir. Use this equation. We are having this value and this value. So we can calculate this one, right? For calculating this leakage impedance drop, normally we apply which formula? We apply this formula. That means we have to know the actual leakage impedance value and we have to know the corresponding current. Then if we multiply this leakage impedance and the current, then we can find the leakage impedance drop. But if the per unit value of leakage impedance is given, then normally from nameplate data we can have this value. Okay, so we can directly calculate the voltage drop, leakage impedance drop. That is one advantage of this per unit system. Is it clear? Yes, sir. Let me consider another advantage. So suppose REL, that is the per unit winding resistance referred to low voltage side. So this is actual winding resistance referred to low voltage side, and this is per unit winding resistance referred to low voltage side. Okay, and ZVL is the base value of leakage impedance from low voltage side. Okay, so these are given. So again we can write this. So REL IBL by ZBL IBL, which is equals to REL IBL into VBL. If we again multiply this by IBL, then we can have IBL square REL VBL IBL. So VBL IBL, what is this? This is the KVA rating or VA rating. Okay, either KVA rating or VA rating. KVA can be converted into VA by multiplying by 1000, and IBL square REL, what is this?
Copper loss.
Copper loss. So if this per unit winding resistance referred to any side is given, then we can directly calculate this copper loss using this KVA rating which is given in nameplate, and if the per unit value of winding resistance is given. This is another advantage of this per unit system. So ohmic loss at rated current can be calculated using this formula, right? Here one example is given. So 10 kVA is the power rating and these are the voltage rating, and REH in per unit is given 0.18 per unit. Okay, so ohmic loss will be 1.8% of this 10 kVA, which is 180 watt, that we can calculate directly, right? Is it clear?
Yes, sir.
Okay, so please note down this problem and try to solve it by yourself. take a snapshot. Done?
Yes, sir.
Okay. Time is over today up to this.